video in our algorithms series. And what I'm gonna do in this video is that I will try to solve these questions, and I won't do it in an intuitive way. I will just use math, and by doing so, we will determine whether, for example, one question is the big O of another for all of these. The first, second, third, fourth, and fifth question. So, in the beginning, this is a quiz from the Coursera, a course called Algorithmic Toolbox. It's a specialization, and it's the quiz about big O notation. But before diving into the questions, I want to um, talk about what is big O, and I want to talk about the formal definition of a big O. Big O is a metric that tells us how our algorithm performs. Like, for example, how many operations does our function execute um, with respect to the input size. We're trying to measure how the number of executions grows as we increase the input size. I'm not going to the detail. I will just give you the formal definition. So it says here Fn is big O of Gn when we can find constant C and we multiply it by the Gn, and it's bigger than Fn for all n's. For all n's. But it's just not for every n. We have to find some other constant n, and this n should be this n should be smaller than the input size at some point. And I will explain it. What does it mean really? So once we find these constants, then it means that this function is the big O of this function. And let's try to find that here. This is our first function. Is it true that log 2n is the big O of n squared? And let's try to find it. In that case, Fn will be log 2n, and Gn will be n squared. And we're trying to solve this equation. Log 2n. And let's separate C. We can divide both sides by n because n is a positive number. Because n symbolizes the number of the input size, and input size cannot be negative, and number of executions as well. So that's why n is a natural number. So S is bigger than log 2n divided by n squared. N squared. Okay. And we want to examine this. And we can further simplify it by saying, okay, we are doing this oh, no, we're not going into that. Okay, so we have this, and this is the division. And we want to observe this as n grows, In simple, in other words, n goes to infinity. Why n goes to infinity? Because we're interested, for example, when as we increase the input size, will there be a point? That c becomes a larger than this division, and after that point, it doesn't matter how uh, much we increase the input size, that c will stay the same and this equation will hold true. This is a very important point. I am repeating it again. As n, the question we are asking is, as n grows to infinity, is there a point where c becomes bigger than this division, and after that point, it doesn't matter how much we increase the input size. In other words, how much we increase the n, c stays the same and this equation still holds true. And let's analyze that answer. Let's try to find an answer. And also that point where c becomes bigger than this division, and then of course at that point n should be a specific number, and we call that specific number n. And once we find this specific number n, what it means that after this point, as we increase n, the c stays the same and this equation still holds true. So that's why n should be at least this number, and then as we grow n, n should be smaller than n, and after the point when n reaches this n, then this should hold true. And after that point, n is equal to big N, it doesn't matter how much we increase this small n, this equation will still hold true. Now let's analyze this. So as n goes to infinity here, n goes to infinity, we cannot calculate this division because n goes to infinity. There is the denominator becomes an infinite number, so we cannot find a real value for this equation. But we're interested in what does it get closer to as we increase n. And we're simply trying to find log 2n squared. And without really calculating it, we can actually calculate this, and it will be 1 n ln 2 in the denominator, and then it will be 1 n squared. So we have actually what we're doing, we are using a Laplace theorem. Was it Laplace? I'm not sure. So the theorem was saying like if we take the derivative of this and this, and the limit should be the same. Okay. Okay. Now it becomes 1 over n cubed. And you can see that as n goes to infinity, this goes to infinity. Oh, sorry, it doesn't go to infinity, it goes to 0. Sorry. So it goes to 0. So as n grows, then if this part gets closer to 0, then we can definitely find c that will be bigger than this, because we at some point we find c, let's say, and as we increase n after that point, this part will be smaller and smaller and smaller. So c will still be bigger than this division. And the point where c becomes equal to this division, then that point we write it n is n. So this is what is n, and for this function we can say that yes, this is the big O of O(n) squared. Yes, that was true. I was just a bit confused at some point. So this is yes. It's the big O of n squared. And let's look at this question now. And we're trying to do the same thing here. C(n), we have C n, it should be bigger. Oh, sorry. Cn and log 2n. And let's do that. Let's do that. We what we can do, we can write these both as and this one we can write this as 2 log 2 n, and these are, it's 1, and then we have this, and we can also get rid of these, and then we have 2cn bigger than n. And let's observe this. Okay, let's write it here. And let's find c. C is divided by 2n. And let's find the limit of this as n goes to infinity. What's happening here? What is happening here is, let's divide everything by n. Then it will be n minus 1. divided by 2. And as n goes to infinity, this goes to infinity. If this goes to infinity, then this also goes to infinity. So we as you can see, we cannot find c, and we cannot guarantee a point after which c always will hold true for n, because this is growing to infinity, and if it's growing to infinity, there won't be a point c after that it is not bigger, because it always goes bigger. It doesn't matter what we choose for c, we can always find a bigger value for this part because it goes to infinity. And because of that, no, this is not big O. And let's look at the third question. The third question is n squared n cubed. Let's try to find this. Okay, by definition we should have cn cube n square, and then let's find c is n square divided by okay n square n square, and then we have what is c is bigger than this, then what we are having here, c is 1 n, right? Okay, because c goes, yes, c is bigger than n square. Okay, now we have this. So as n goes to infinity, it becomes 0. This, and it means that if it goes closer to 0 and it's decreasing, there will be a point where a point n, like we increase n1, n2, n3, n4, n5, and at this n it will be equal to c, and after that point, as we increase more and more, the c should stay the same, but it will be decreasing. So it will hold true for all of the numbers bigger than this number, for all of the n's that is bigger than this, and it will hold true. So this is the big O of this, and let's check that. The question, can we do that again? Resume assignment. Okay. Oh, no, wait, not this one. Previous. Try again. Okay, we had yes, we had okay, we had yes, no, yes, yeah, these should be true. Submit. Yes, these three are correct. Let's look at other question. The last, yeah, this one. Let's look at this one, the fourth question. The fourth question says n we're checking this. And this will be the last example, because you do every example with the same way, and we say, okay, C, is there a point where n this is bigger than n, and let's divide both sides by square n. It will be s square n, and as n grows, it goes to infinity, then no, this is no, it's not the big O. And we say yeah, this won't be the big O, because we cannot find C that will stay the same after some n equals to n, and then after all of the n, C should stay the same and this equation will hold true. That's not possible.